Welcome to our educational journey through the intricate world of circuit analysis. Understanding circuits is crucial for any aspiring electrical engineer, as these networks of electrical elements form the backbone of modern technology, from simple gadgets to complex machinery. Without proper laws and methods, analyzing circuits can be daunting, often leading to confusion and errors. By mastering circuit analysis, you'll be equipped to break down and understand even the most complicated electrical networks. Throughout this video, we'll explore Kirchhoff's laws, which simplify the process and provide a systematic approach to tackling circuit challenges. Whether you're a student, an enthusiast, or an educator, understanding these laws is key to unlocking your potential in electrical engineering. Let's dive into the fascinating world of circuit analysis and discover how Kirchhoff's laws can transform your understanding of electrical networks, guiding you to accurate solutions. Welcome to our journey into the fascinating world of circuit analysis. Today, we dive into Kirchhoff's laws, formulated by Gustav Kirchhoff in the 19th century, which are essential tools for simplifying and mastering circuit analysis. Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL, help us understand how electrical currents and voltages distribute within a network. Without these guiding principles, solving complex puzzles would be nearly impossible. As fundamental building blocks, these laws empower us to break down and analyze intricate circuits with confidence. Whether you're encountering electric circuits for the first time, seeking deeper knowledge, or teaching this subject, mastering Kirchhoff's laws is crucial. Let's set the stage for an exciting exploration and uncover the simplicity and power of these laws, demystifying circuit analysis. Let's get started. Kirchhoff's current law, KCL, is a fundamental principle in electrical engineering, rooted in the conservation of charge. According to KCL, the total current entering a junction must equal the total current leaving the junction, ensuring that electric charge is neither created nor destroyed. By applying KCL, we can solve for unknown currents by setting up equations that sum the currents at a given node. This process makes complex networks more manageable and predictable. Mastering KCL allows us to systematically approach and solve intricate circuits. As we move forward, you'll see how KCL is applied to specific examples, reinforcing your understanding and confidence in tackling circuit problems. Let's apply Kirchhoff's current law to a simple circuit. First, we'll identify a node where multiple currents converge. According to KCL, the sum of currents entering the node must equal the sum of currents leaving it. We'll break down this process step by step. Start by labeling all known currents and identifying the unknowns. Next, set up an equation where the total incoming currents equal the total outgoing currents. Solving this equation will reveal the unknown currents. This step-by-step node analysis demonstrates how Kirchhoff's current law works in practice. As we move forward, you'll see how using both Kirchhoff's laws together helps in handling more complex circuits. Stay tuned as we delve deeper into Kirchhoff's voltage law next. In this segment, we're diving into Kirchhoff's voltage law, commonly abbreviated as KVL. Simply put, Kirchhoff's voltage law asserts that the sum of all electrical voltages around a closed loop in a circuit equals zero. This fundamental principle is vital in loop analysis, serving as a cornerstone in understanding how voltage behaves in electrical networks. Imagine tracing a closed path around any circuit loop. According to KVL, the algebraic sum of the potential differences encountered along this loop always balances out to zero. This means that energy is conserved within this loop, a concept you'll find applicable in numerous practical scenarios. We'll apply KVL to solve complex circuits in a systematic way. By summing the voltages around a loop, we'll derive equations that help determine unknown values and analyze the circuit thoroughly. As we move forward, you'll see how KVL works in practical applications, making circuit analysis more intuitive and manageable. Stay with us as we explore examples that put this powerful law to work. Now that we've covered the basics of Kirchhoff's voltage law, let's put it into action. Imagine a simple electrical circuit with a closed loop. Using KVL, we can solve for the unknown voltages within this loop. First, identify all the components in the loop, resistors, batteries, and so forth. Next, we'll assign a direction for the loop current, typically clockwise. With KVL, the sum of all the voltages around this loop must equal 0. So starting at one point in the loop, we add up the voltages, taking care to note whether each component's voltage is positive or negative based on our chosen direction. For instance, if we encounter a resistor, we use Ohm's law, V equals IR, to calculate the voltage drop across it in the current's direction. If we pass through a battery from negative to positive, we add its voltage as a positive value. Once we've summed all the voltages, we set the equation to 0 and solve for the unknown voltage. This systematic approach makes circuit analysis more manageable. As we move forward, you'll see how combining KCL and KVL can tackle even more complex circuits. In analyzing real-world circuits, we often use both Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL, together. KCL helps us understand the behavior of currents at various junctions, while KVL assists in analyzing the voltages around closed loops. By combining these two powerful laws, we can systematically break down and solve for unknown parameters in highly complex circuits. This synergy between KCL and KVL allows us to tackle otherwise difficult problems, opening up a deeper understanding and capability in circuit analysis. As we move forward, you'll see these laws in action, showing how they simplify even the most complicated electrical networks. Let's analyze a simple real-world circuit using Kirchhoff's laws. Imagine a basic circuit with a power source and a couple of resistors. We start by applying Kirchhoff's current law, KCL, which tells us that the total current entering any junction equals the total current leaving. After identifying our junction points and summing the currents, we apply Kirchhoff's voltage law, KVL. KVL states that the sum of all voltages around a closed loop equals 0. By analyzing our loop, we'll add up the voltage drops across each component. Using these two laws, we can solve for the unknown currents and voltages in the circuit, simplifying our analysis and ensuring accuracy. As we move forward, you'll see how these fundamental principles apply to more complex circuits. Ready for a more challenging scenario? Stay tuned as we tackle a complex real-world example next. Now, let's tackle a more complex real-world circuit using Kirchhoff's laws. Start by identifying the nodes and loops within the circuit. Using Kirchhoff's current law, KCL, we analyze the current flowing through each node, ensuring the sum of currents entering any node equals the sum of currents leaving it. Next, we apply Kirchhoff's voltage law, KVL, which states that the sum of all voltages around any closed loop in a circuit is equal to 0. We'll go through each loop, summing the voltages, and solving for unknown variables. Combining these laws breaks the circuit into manageable parts, ensuring accurate calculations. It may seem challenging at first, but with practice, you'll see how these laws simplify complex circuits significantly. As we move forward, you'll see how these principles apply to even more intricate circuits, showcasing the power and efficiency of Kirchhoff's laws in real-world applications. To recap, Kirchhoff's laws are essential tools in circuit analysis. Kirchhoff's current law, KCL, tells us that the total current entering a junction equals the total current leaving it, helping us balance and solve for unknown currents in complex circuits. Kirchhoff's voltage law, KVL, states that the sum of all voltages around a closed loop equals 0, allowing us to determine unknown voltages. Using both KCL and KVL together simplifies the process of circuit analysis, making it easier to understand even the most complex electrical networks. Remember, these laws aren't just theoretical concepts. They're practical tools used every day in electrical engineering. They provide a clear roadmap for analyzing and solving circuits logically and systematically. As we move forward, keep these fundamental principles in mind. Mastering Kirchhoff's laws enhances your ability to tackle real-world engineering problems with confidence and precision. If you found this video helpful, make sure to subscribe and follow for more educational content on electrical engineering. Engaging with our channel ensures you don't miss out on in-depth explanations and useful tips for mastering complex concepts. Continue your journey of learning with us. Stay tuned for more insights into the world of circuit analysis and beyond. Remember, knowledge is power, and every circuit problem becomes a stepping stone towards becoming a more confident and proficient engineer. So don't forget to hit that subscribe button and follow us to stay updated. Together, we can light up the path of understanding, unlocking the mysteries of electrical engineering, one step at a time.